If the universe is slowly running out of fuel, why does the night sky still seem crowded with light? That simple question hides one of the deepest tensions in modern cosmology. Every star you see is powered by nuclear reactions that cannot last forever, and yet from Earth, the cosmos still looks active, luminous, almost abundant. In this video, we step carefully into that contradiction. We explore where cosmic light truly comes from, how long it can continue, and what it means for a universe that has already passed its most productive era. What appears stable on human timescales turns out to be fragile when measured across billions of years. As the picture widens, familiar ideas, stars, gravity, even time itself, begin to feel less permanent, more conditional. Distances stretch across light years, each photon arriving as a message from a past that no longer exists in the same form. What we see is not the present universe, but a delayed record of processes already winding down. From there, the discussion moves into part one. Why is the universe still bright if it is already dying? Where the first signs of tension begin to appear within the data itself. If the universe is running out of fuel, why does the night sky still appear crowded with light? That question is unsettling because it points directly at a mismatch between what cosmology measures and what human perception receives. Modern astronomy is clear on one fact. The rate at which the universe forms new stars reached its maximum billions of years ago and has been declining ever since without reversal. And yet when we look upward, we still see galaxies filled with stars, nebulae glowing, and deep space surveys revealing vast numbers of luminous systems. The contradiction is only apparent, but resolving it requires stepping into the full timescale of cosmic evolution, where light, gravity, and expansion operate very differently from everyday intuition. The idea that the universe is already in decline did not emerge suddenly. In the 1960s and 1970s, astronomers began to assemble the first coherent picture of cosmic star formation history. Early surveys hinted that distant galaxies, seen as they were billions of years ago, appeared far more active than nearby ones. Over time, this pattern became unmistakable. By the early 2000s, large observational programs using ground-based telescopes and space observatories showed that the universe formed stars most rapidly, roughly 10 billion years ago. Since then, the overall rate has fallen by more than an order of magnitude. This is not a subtle effect hidden in statistical noise. It is one of the most robust trends in observational cosmology. The evidence comes from multiple independent methods. Astronomers measure star formation by tracking ultraviolet light from massive young stars, infrared emission from dust heated by stellar nurseries, and specific spectral lines produced by ionized gas. Each method has its own uncertainties, yet all converge on the same conclusion. Surveys conducted by NASA and ESA, along with ground-based observatories, reveal a universe that was far more efficient at converting gas into stars in its earlier epochs than it is today. The decline is smooth, gradual, and global. One might reasonably ask why this decline matters if stars are still shining everywhere we look. The answer lies in understanding what light actually represents. Light is not a real-time signal. Every photon that reaches Earth has traveled for a finite duration, sometimes for billions of years. When we observe a galaxy 10 billion light-years away, we are not seeing it as it is now, but as it was when the universe was much younger. In this sense, the sky functions as a layered archive. Brightness does not imply current vitality. It records past activity preserved by the finite speed of light. This effect alone explains much of the apparent contradiction. The distant universe appears bright because it truly was brighter in the past. Deep surveys using the James Webb Space Telescope have made this especially clear. Webb's infrared sensitivity allows astronomers to observe galaxies from the first few billion years after the Big Bang, an era when star formation was intense and widespread. These galaxies are compact, gas-rich, and highly productive forming stars, at rates far exceeding those of typical galaxies today. When these ancient systems dominate deep images, they create an impression of abundance that does not reflect present-day conditions. Closer to home, the decline is equally evident but easier to overlook. Our own galaxy forms only a few solar masses of stars per year. In cosmic terms, this is modest. Billions of years ago, galaxies like the Milky Way formed stars several times faster. The raw material for star formation, cold hydrogen gas, has been steadily consumed or rendered inaccessible. Each generation of stars locks matter into long-lived remnants, white dwarfs, neutron stars, and black holes. Over time, less gas remains available to collapse into new stars. This leads to the first major hypothesis behind the central paradox: star formation is already in terminal decline, despite visual abundance. The term terminal here does not imply an imminent end on human timescales. Instead, it means that the overall trend is irreversible under known physics. There is no mechanism that replenishes hydrogen on galactic scales once it has been fused into heavier elements. Stellar evolution is one-way traffic. Nuclear fusion converts light nuclei into heavier ones, releasing energy, but it does not recycle fuel in a way that supports indefinite starbirth. Historical examples make this clearer. In the early 20th century, before nuclear fusion was understood, astronomers debated how stars could shine for billions of years. The solution emerged only when physicists realized that mass could be converted into energy through fusion, as described by relativity. That insight explained stellar longevity, but it also imposed a hard limit. Fusion consumes fuel. Even the longest-lived stars, the small red dwarfs, will eventually exhaust their hydrogen after trillions of years. The process is slow, but it is not optional. The second hypothesis addresses a subtler factor. Cosmic expansion quietly suppresses gravity's long-range cooperation. Gravity has not weakened as a force, but the expanding universe changes how matter can respond to it on the largest scales. Since the late 1990s, observations of distant supernovae have shown that cosmic expansion is accelerating. This acceleration, commonly attributed to dark energy, stretches space itself. As space expands faster, matter becomes more isolated. Regions that might once have collapsed together under gravity are gradually pulled apart. This effect does not tear stars or galaxies apart. Local systems remain gravitationally bound. However, it does limit the formation of new, large-scale structures. Gas clouds that are too diffuse cannot overcome the expanding background to collapse. Over time, expansion acts like a quiet counterbalance to gravity, not by destroying existing structures, but by preventing new ones from assembling. In this way, expansion does not end star formation directly. It reduces the universe's ability to restart it. Observational support for this idea comes from the distribution of galaxies and gas. Modern surveys show that star formation today is concentrated in dense environments where gas has already settled into deep gravitational wells. Vast regions of intergalactic space contain gas that is too thin to ever collapse again. As expansion continues, these regions grow larger, not smaller. The universe becomes increasingly structured into isolated islands of matter separated by expanding voids. It is important to emphasize that none of this implies sudden darkness. Stars already formed will continue to shine for immense durations. The night sky appears bright because stellar lifetimes are long compared to the timescale of decline in formation. This mismatch in timescales is crucial. Star formation peaked and declined over billions of years, while individual stars can shine for billions or even trillions of years. The result is a long afterglow, a universe that looks active long after the processes that sustain that activity have begun to fail. This is not speculation, but a conclusion supported by models tested against observation. Simulations of galaxy evolution, constrained by real data, reproduce the same decline seen in surveys. When researchers adjust the models to force continued star formation indefinitely, they conflict with observed gas distributions and stellar populations. The evidence points consistently in one direction. A historical parallel can be found in the understanding of stellar populations in galaxies. In the 1950s, astronomers realized that galaxies contain different generations of stars. Older populations are redder and dimmer, younger ones bluer and brighter. By studying these populations, scientists reconstructed the formation histories of galaxies. The same approach applied on cosmic scales reveals a universe that formed its stars early and has been slowing down ever since. If star formation is declining and expansion suppresses gravitational cooperation, why does the universe not already look dimmer nearby as well as far away? The answer lies in the sheer inertia of cosmic systems. Once stars form, they persist. The decline is visible statistically, not dramatically. There is no single event that marks the transition. Instead, there is a gradual shift in probabilities. Fewer stars are born per unit time, but those already born continue shining, giving the appearance of stability. The universe can look alive long after the processes that sustain it have begun to fail. Light is not a guarantee of renewal. It is a record of past success, not proof of future potential. From a physical standpoint, the universe is not approaching darkness because stars are suddenly extinguishing, but because the conditions that allow new stars to form are slowly disappearing. Every observation reinforces this view, from ultraviolet surveys mapping young stars to infrared observations tracing cold gas from supernova counts to galaxy simulations. The same story emerges. The decline is quiet, persistent, and global. It does not announce itself with spectacle. It simply continues. With that realization in place, brightness no longer reads as a sign of vitality, but as a delayed message arriving from an earlier state of the universe. Once light is understood this way, the idea of an ending becomes less straightforward. In a cosmos where illumination can persist long after creation has slowed, even the word end begins to lose its usual meaning. Part 2. What does the last year of the universe mean in physical terms? When cosmology speaks of a last year whose clock is actually being used, and what physical process is allowed to decide that time is running out? A year sounds like an everyday unit, a familiar loop of seasons and calendars, but the universe does not carry a wristwatch, and it does not share a single timekeeper across all of space. In astronomy, even the word now is slippery, because every observation arrives late. The light from the sun is about 8 minutes old when it reaches you. The light from the nearest stars is years old. The light from distant galaxies can be billions of years old. So if we say the last year of the universe, we have to be careful, because a year cannot be a universal date stamped across everything that exists. It has to be tied to a definable physical threshold, something that can be described without depending on a human calendar. A useful way to make this phrase scientific is to treat a year as a marker of energy production, not a marker of human routine. The bright universe is bright for a simple reason that is also a strict limitation. Stars shine because nuclear reactions in their cores release energy, and those reactions run on fuel that is not replenished. In practice, when cosmologists talk about the luminous era, they mean the long interval in which starlight is still being generated by fusion. The phrase last year becomes a shorthand for the final stage of that era, when the last sustained fusion reactions capable of producing visible and infrared light finally stop everywhere they can stop. This is where the first hypothesis becomes concrete. The final year is defined by the extinction of hydrogen fusion. Hydrogen fusion is not a vague metaphor. It is a specific set of reactions, tested in laboratories, anchored in nuclear physics, and confirmed by stellar observations. In sun-like stars, hydrogen fuses primarily through the proton-proton chain. In more massive stars, hydrogen fusion proceeds through the carbon-nitrogen-oxygen cycle. These processes convert hydrogen into helium, releasing energy that eventually escapes as light. The important detail is that hydrogen fusion is the beginning of the bright story for most stars, and when it ends, the star's ability to shine collapses into a different mode. It may continue with helium fusion, carbon fusion, and heavier burning stages if the star is massive enough, but those later stages are shorter and rarer in the cosmic inventory. For the overwhelming majority of stars, especially low-mass stars, the long, luminous life is dominated by hydrogen fusion. If you want a historical anchor, there is a reason hydrogen fusion carries such weight in astrophysics. In the early 20th century, astronomers knew stars radiated enormous power, but they did not know the engine. Chemical burning could not support a star for even a small fraction of the sun's known age. Gravitational contraction alone could not account for the billions of years required by geology and biology. The solution sharpened in the 1930s when nuclear physics matured and astrophysicists, including Hans Bethe, worked out reaction pathways that could plausibly operate in stellar cores. What turned those pathways into accepted science was not poetry or philosophy, but consistency across evidence. The predicted energy release matched stellar luminosities. The predicted temperature dependence matched the observed relation between mass and brightness. Neutrinos, produced in the proton-proton chain, were later detected from the Sun, and their properties connected directly to fusion models. Step by step, the star became a measurable nuclear system, rather than an unexplained lamp. So if the last year is defined by the extinction of hydrogen fusion, what does that mean in time units we can name? It means we identify which objects can sustain hydrogen fusion the longest, and we ask when the final one exhausts its usable core hydrogen. The answer is not a dramatic explosion. It is a slow fade over extreme timescales, dominated by the smallest, most efficient stars. Red dwarfs with masses far below the sun's burn fuel slowly because their core temperatures are lower and their luminosities are small. Stellar models indicate lifetimes that can reach trillions of years for the least massive red dwarfs that still sustain fusion. That statement is not a guess pulled from atmosphere. It is the outcome of well-tested stellar structure equations combined with nuclear reaction rates calibrated against real stars observed across the Milky Way. The uncertainty lies in details at the extreme end, because no red dwarf has had time to exhaust its hydrogen in the current age of the universe. But the direction is clear. The longest-lived fusion engines are low-mass stars, and the last steady hydrogen fusion should belong to that class. However, even this apparently clean definition has a hidden complication that forces us to sharpen language. The universe does not offer a single synchronized clock that ticks the same for every observer. In general relativity, time is local. A clock's rate depends on motion and gravitational potential. In cosmology, when scientists say the universe is about 13.8 billion years old, they usually mean cosmic time in a particular model measured for an observer at rest, with respect to the average expansion often described using the frame where the cosmic microwave background looks statistically isotropic. This is a powerful convention, and it is extremely useful, but it is still a convention built on a model of spacetime. The idea of the last year cannot mean one universal moment that all regions experience simultaneously in the same sense. So we refine again. The last year of the luminous era can mean the last interval measured in cosmic time, during which any stable fusion source exists anywhere in the observable universe. This definition is operational. It can be tied to a model, to a scale factor, to expansion history, and to the evolution of stellar populations. It avoids the impossible demand for a single global clock while still yielding a clear physical criterion. The luminous era has already passed its point of no return. This does not mean the universe is about to go dark. It means the processes that increase the total production rate of starlight have already peaked and are declining in a way that is not expected to reverse under known physics. This is a statement about the global star formation rate density, not about the brightness of individual stars. Observations across multiple wavelengths show that the universe formed stars most rapidly when it was much younger, and since that peak, the average rate has dropped substantially. The practical reason is fuel logistics. Cold gas reservoirs are being used up heated or locked into remnants. Mergers and interactions that once triggered bursts of star formation are less frequent as large-scale structure growth slows. The accelerating expansion associated with dark energy increases the isolation of gravitationally bound regions over time, limiting the supply routes by which diffuse gas could later be gathered into new star-forming systems. This is where the phrase "last year" becomes more than a dramatic title. It becomes a technical prompt. If the luminous era has passed its point of no return, then the last year is not an unpredictable, sudden event. It is the tail end of a long, controlled decline. In that picture, the date is not defined by what we see in the sky tonight, because the sky is a mixture of different times. It is defined by the future availability of free energy sources capable of producing high-quality photons in large quantities, primarily from fusion. When those sources become extinct, the universe may still contain radiation, but the character of that radiation changes. It becomes dominated by cooling remnants, by faint thermal emission, and eventually by much lower energy backgrounds. This is also a good place to handle a common confusion with careful language. When people hear last year, they often imagine a last flash, a last sunrise, a last candle. Physics does not owe us a single closing scene. Stellar deaths are local. They occur at different times, in different environments, and under different histories of chemical enrichment. Even the last hydrogen-fusing star, if it is a low-mass red dwarf, does not end in a supernova. It cools. It dims. It changes spectral output. The universe does not have a switch labeled on and off. It has rates, distributions, and thresholds. To keep the concept anchored, it helps to connect to the way astronomy measures time in the first place. The distance ladder, built from parallax variable stars and standard candles, allowed astronomers to convert observed brightness and redshift into a history of expansion. The work of Henrietta Leavitt on Cepheid variables provided the method. Edwin Hubble used it to show that galaxies lie far beyond the Milky Way and that the universe is expanding. Much later, Type Ia supernovae were used as standardizable candles to measure acceleration. Each step in this story took a human lifetime, but each step also built a machine for measuring the universe's clock. That machine is not a single device. It is a network of methods, cross-checked and calibrated, that lets us translate the sky into a timeline. Within that timeline, the phrase "last year" can be treated as a boundary condition. It is not meant to suggest that cosmologists know the exact calendar year when the last star turns off, because that would require knowing future stochastic events in galaxy evolution. Instead, it is meant to isolate the physical requirements for starlight to exist at all, and to show which requirements are being steadily removed. Hydrogen availability, cooling pathways for gas clouds, gravitational binding in galaxies, the balance between collapse and expansion, nuclear reaction rates. Each of these can be measured or constrained today, and each can be projected forward with models that match the existing universe. At this point, a line from Steven Weinberg is often quoted because it captures the starkness of the framework, even if we keep our focus on physics rather than interpretation. The more the universe seems comprehensible, the more it also seems pointless. In a scientific context, the value of this sentence is that it reminds us how indifferent the equations are to human intuition. They describe what happens, not what we expect to happen. They let us define a last year in physical terms, even when the phrase sounds like it belongs to a story rather than a dataset. The last year is a definition problem. It depends on what you choose to call the luminous era, on which physical process you decide counts as the production of starlight, and on which clock you use to label time in an expanding relativistic universe. If you tie it to fusion, you tie it to the life cycle of stars. If you tie it to the global star formation rate, you tie it to the irreversible decline of star birth. Both are valid, but they do not produce the same emotional picture, and they do not produce the same technical boundary. One is about the last source. The other is about the end of renewal. And another pressure emerges, naturally, from the physics itself. If the idea of a final year depends on which objects can continue fusing hydrogen for the longest time, the problem narrows into a single concrete test of stellar behavior, one that can be stated plainly without drama or metaphor. It comes down to a simple physical constraint. Which star is actually capable of being the last one? Part 3. Which star is physically capable of being the last one? If every star must die, which kind survives long enough to be the final source of light? To answer that question, astronomy does not begin with speculation, but with elimination. Massive stars burn bright and die young. Intermediate stars, like the Sun, live longer but still exhaust their fuel on timescales far shorter than the future of the universe. What remains, after every faster burning option is ruled out, are the smallest stars that nuclear physics allows to exist at all. These are the red dwarfs, objects so modest in mass and luminosity that for much of the history of astronomy they were overlooked, underestimated, and sometimes dismissed entirely. Red dwarfs dominate the stellar census of the universe. More than 70% of all stars in the Milky Way belong to this class. They have masses between roughly 8% and 50% of the Sun's mass. Below that lower threshold, nuclear fusion cannot ignite, and the object becomes a brown dwarf, never truly a star. Above it, fusion proceeds, but at a pace that changes dramatically with mass. This narrow range produces the longest-lived nuclear engines nature knows. The physics behind their longevity is well understood and grounded in observation. A star's lifetime is not set by how much fuel it has alone, but by how quickly it spends that fuel. Red dwarfs burn hydrogen at an extraordinarily slow rate because their core temperatures and pressures are lower than those of larger stars. The nuclear reactions still occur, but less frequently. At the same time, red dwarfs are fully convective. Their interiors circulate material efficiently, bringing fresh hydrogen from outer regions into the core. Larger stars, including the Sun, do not enjoy this advantage. They exhaust hydrogen in their cores, while significant reserves remain locked away in outer layers inaccessible to fusion. This combination of slow burning and efficient mixing extends red dwarf lifetimes to scales that stretch human intuition. Stellar evolution models, constrained by nuclear reaction rates, measured in laboratories, and validated by star counts in clusters of different ages, indicate that the smallest red dwarfs can sustain hydrogen fusion for about 10 trillion years, roughly 10,000 billion years. This figure does not come from guesswork. It arises from equations that successfully predict the properties of stars we observe today, and from population models that match what telescopes actually see. What makes this result especially striking is that the universe itself is far younger. At approximately 13.8 billion years old, it has not existed long enough for a single red dwarf to complete its hydrogen-burning lifetime. Every red dwarf that has ever formed is still in its main sequence phase. None have yet reached the point of fuel exhaustion. This is not a gap in data that could be filled by a better telescope. It is a fundamental consequence of cosmic youth. Observations by NASA and ESA have confirmed the stability of red dwarfs across a wide range of environments. Star clusters, with ages of billions of years, show red dwarfs that are essentially unchanged. Their luminosities, temperatures, and spectra match theoretical expectations precisely. More recently, data from the James Webb Space Telescope have extended this confirmation into earlier cosmic epochs, revealing red dwarf populations in ancient galaxies that already look remarkably mature. Given this evidence, the first hypothesis becomes clear. Ultra-low-mass stars fade without any dramatic signal. When a red dwarf finally exhausts its hydrogen, it does not explode, it does not collapse. It does not announce its death across interstellar space. Instead, fusion slows, luminosity decreases, and the star gradually cools into a dark, inert remnant. The process is smooth, continuous, and local. There is no universal marker that declares one star to be the last. The universe does not pause to observe it. This behavior stands in contrast to the deaths of massive stars which shape much of popular astronomy. Supernovae scatter heavy elements, light up galaxies, and leave behind neutron stars or black holes. Red dwarfs do none of this. Their contribution to cosmic chemistry is minimal, but their contribution to cosmic longevity is unmatched. They persist, quietly converting hydrogen into helium, long after more dramatic stars have vanished. The idea that the last star could be something so faint and unspectacular was not always accepted. In the early 20th century, astronomers focused their attention on bright stars because those were the ones they could study. The Hertzsprung-Russell diagram, which organizes stars by brightness and temperature, revealed that red dwarfs occupied a vast region of parameter space, but their faintness made them difficult to observe in detail. Some early astronomers referred to them as failed stars, not because they lacked fusion, but because they seemed insignificant compared to luminous giants. This view changed as stellar physics matured. Once nuclear fusion was understood, it became clear that brightness is not a measure of importance, but of consumption rate. Red dwarfs were not failures. They were the most efficient hydrogen-burning machines in the universe. Their faintness was not a flaw. It was the reason they would endure. This shift in understanding mirrors a broader pattern in science, where longevity and stability often emerge from systems that operate slowly and conservatively. In planetary science, small, stable bodies preserve records lost on more active worlds. In cosmology, slow-burning stars outlast brilliant ones. The lesson is not philosophical, it is mechanical. Rate matters. However, identifying red dwarfs as candidates for the last star does not end the inquiry. It opens a deeper question which forms the second hypothesis. Stellar physics, at extreme longevity, may deviate subtly from current models. The equations that predict 10 trillion-year lifetimes are robust, but they are extrapolated far beyond the timescales we can test directly. While the underlying physics is well constrained, the boundary conditions are unprecedented. For example, red dwarfs experience magnetic activity flares and stellar winds. Over trillions of years, even weak mass loss could alter their evolution. Current observations show that red dwarfs are magnetically active, especially when young. They flare frequently, emitting bursts of radiation. Over billions of years, this activity declines, but its long-term cumulative effect over trillions of years is not something we can measure directly. There is also the question of chemical evolution. Red dwarfs form from gas enriched by previous generations of stars. Their initial composition influences opacity, energy, transport, and reaction rates. As the universe ages and metallicity increases, future red dwarfs may differ subtly from those forming today. Whether these differences affect ultimate lifetimes is an active area of research. None of these uncertainties undermine the central conclusion. They refine it. They suggest that the exact identity of the last star may depend on details that cannot yet be observed, but the class of objects capable of surviving that long is well defined. It will not be a giant star. It will not be a sun-like star. It will be an ultra-low-mass red dwarf, operating at the edge of what nuclear fusion permits. It is also important to note that the last star need not be unique. There may be many red dwarfs burning hydrogen at extremely low luminosities across the universe at similar times. The concept of the last star is a limit, not an appointment. It marks the end of a category of physical processes, not a singular event. This distinction matters because it reshapes how we think about cosmic endings. There is no final spotlight. There is no universal blackout. There is a gradual thinning of light sources until fusion becomes impossible everywhere. At that point, the universe does not become empty. It becomes quieter in a very specific physical sense. The search for the longest-lived stars has already influenced how astronomers think about habitability and cosmic history. Red dwarfs host many planets. Their longevity suggests that planetary systems around them could exist for trillions of years. At the same time, their early magnetic activity poses challenges for planetary atmospheres. These considerations tie stellar physics directly to broader questions about the universe's capacity to sustain complex systems over time. Yet for the purpose of identifying the last star, habitability is irrelevant. Only energy production matters. Only the ability to fuse hydrogen counts. And by that metric, red dwarfs stand alone. The conclusion that emerges from decades of observation and theory is firm but not final in the philosophical sense. It is final in the physical sense. Given what we know about nuclear fusion, stellar structure, and cosmic evolution, the stars most capable of surviving to the far future are already present today, quietly shining at the bottom of the main sequence. And once that fact is accepted, the focus shifts again. If the final light comes from a star that fades without spectacle, attention no longer rests on the star itself, but on what follows after. Even that slow engine has run its course. What matters then is the state of the universe once the conditions for star formation have fully disappeared. Part 4. Why can the universe no longer build new stars forever? What if gravity is still present but no longer effective? At first glance, the idea sounds contradictory. Gravity has not weakened. Its equations still describe how mass attracts mass with the same precision they always have. Galaxies remain bound. Stars continue to orbit. Nothing about gravity itself has failed. And yet across the universe, the construction of new stars is steadily shutting down. The reason is not that gravity disappeared, but that the conditions allowing gravity to assemble new stars are being quietly removed. To understand why the universe can no longer build stars forever, we must begin with the raw material. Stars form from cold, dense clouds of hydrogen gas. Hydrogen is not simply a fuel. It is the structural prerequisite for star birth. It must be cold enough to lose pressure, dense enough to become unstable, and sufficiently isolated from disruptive forces to collapse under its own gravity. Every successful star formation event satisfies these conditions for a brief moment. Over cosmic time, those moments become rarer. Observations collected by NASA and ESA show that the universe once contained vast reservoirs of cold hydrogen gas. In the early billions of years after the Big Bang, galaxies were compact, gas-rich, and highly interactive. Collisions and close passes between galaxies compressed gas clouds, triggering intense bursts of star formation. This era produced stars at rates far exceeding anything seen today. It was not sustainable, but it was extraordinarily productive. Over time, that hydrogen has been steadily consumed. Each generation of stars converts hydrogen into heavier elements. Some of that processed material is returned to the interstellar medium through stellar winds and supernova explosions, but a significant fraction becomes permanently locked away. White dwarfs trap matter in dense, inert states. Neutron stars compress matter beyond ordinary atomic structure. Black holes remove matter from future participation entirely. Every such remnant is a vault that no longer contributes hydrogen to future star formation. Usable gas becomes permanently locked inside remnants. This is not an assumption. It is a measured accounting problem. Astronomers track the mass budget of galaxies by observing gas, stars, and remnants across cosmic time. The numbers do not balance in favor of renewal. While some gas is recycled, the total amount of cold star-forming hydrogen declines. Gas that is heated by stellar feedback or gravitational shocks can remain too warm and diffuse to collapse again. Gas that falls into deep gravitational wells may never cool efficiently. Over time, the universe becomes poorer in precisely the kind of hydrogen needed to ignite new stars. Historical context sharpens this picture. In the mid-20th century, astronomers debated whether galaxies could sustain star formation indefinitely. Some imagined a steady-state cycle where gas consumption and replenishment balanced out. That view faded as radio astronomy revealed the true distribution of neutral hydrogen. Measurements of the 21-centimeter line showed that galaxies possess finite hydrogen reservoirs. Once those reservoirs are depleted or stabilized against collapse, star formation slows and eventually stalls. The second constraint emerges from a much larger scale, one that does not operate inside galaxies at all. It comes from the expansion of the universe itself. Since the late 1990s, observations of distant supernovae have shown that cosmic expansion is accelerating. Space is not merely stretching, it is stretching faster over time. This accelerated expansion, commonly attributed to dark energy, alters the long-term fate of matter. Gravity still acts locally. Within galaxies and clusters it dominates, but on larger scales expansion wins. Regions of matter that are not already gravitationally bound are being carried apart faster than gravity can pull them together. This does not tear existing stars or galaxies apart, but it does something more subtle and more final. It prevents new large-scale collapses from ever starting. Expansion prevents matter from ever collapsing again. The phrase sounds dramatic, but its meaning is precise. For a gas cloud to collapse into a star, it must overcome not only its internal pressure, but also the background expansion of space. In the early universe, expansion slowed enough for gravity to assemble galaxies and clusters. Today, expansion is accelerating. As a result, diffuse matter is increasingly isolated. The distances between unbound regions grow too quickly for gravity to coordinate collapse. Data from the James Webb Space Telescope have reinforced this understanding by mapping star formation across cosmic time. Webb's infrared vision allows astronomers to observe star-forming regions in very distant galaxies, capturing epochs when star formation was vigorous. When these observations are combined with surveys of nearby galaxies, the trend is unmistakable. Star formation is retreating into the densest, most gravitationally secure environments. Vast volumes of space contain gas that will never form stars again. It is important to emphasize what expansion does not do. Expansion does not destroy stars. It does not extinguish light. It does not reach into galaxies and tear them apart. Instead, it shapes the future by setting boundary conditions. It decides which regions of matter can still interact and which are forever isolated. In this sense, expansion acts not as a force of destruction, but as a limit on construction. The distinction matters because it explains why the universe can still look active while losing its creative capacity. Stars that already exist continue shining for billions or trillions of years. Their light dominates the sky. Meanwhile, the processes that would create replacements are quietly being disabled. Expansion stretches the universe into a pattern of islands, each island containing a finite supply of gas and a finite future of star formation. This insight was not always obvious. In the early days of cosmology, expansion was treated as a background feature, not as an active participant in astrophysical processes. That changed as simulations improved. When cosmologists began modeling galaxy formation within expanding spacetime, they discovered that accelerated expansion fundamentally alters the fate of structure formation. The equations showed that once expansion reaches a certain dominance, new large-scale gravitational collapse effectively halts. Observations later confirmed this prediction. Another layer of evidence comes from the chemical evolution of galaxies. As star formation slows, the production of new heavy elements declines. This affects cooling processes, which depend on the presence of metals to radiate energy away. Gas without sufficient cooling pathways cannot collapse efficiently. In this way, chemical enrichment both enables and ultimately limits star formation. The universe builds the tools it needs to make stars, then gradually removes the conditions under which those tools can be used. At this stage, the picture is dense but coherent. Hydrogen is being consumed and locked away. Expansion is isolating matter. Cooling becomes less effective. Each factor reinforces the others. None require speculation beyond established physics. Each is supported by observation. Expansion does not destroy stars. It prevents them from being born. The universe is not approaching darkness because gravity failed, but because gravity has fewer opportunities to act. A useful analogy handled carefully can clarify the point without diluting it. Imagine a city with functioning construction equipment, but no available land and no supply of building materials. The machines still work. The laws governing construction have not changed, but no new buildings appear. The limitation is not capability, but access. In the universe, gravity remains the builder, but hydrogen and connectivity are being withdrawn. This understanding also explains why star formation decline is irreversible under known physics. There is no mechanism that recreates primordial hydrogen on cosmic scales. There is no process that reverses accelerated expansion. There is no hidden reservoir waiting to be unlocked. The equations governing nuclear fusion, thermodynamics, and space-time geometry all point in the same direction. For decades, astronomers tested alternative possibilities. Could inflows from intergalactic space resupply galaxies indefinitely? Could mergers restart star formation cycles? Could unknown physics alter expansion? Each idea was evaluated against data. None survived without contradiction. The decline persisted across environments, epochs, and observational techniques. As a result, modern cosmology treats the end of star formation not as a hypothesis, but as a projection grounded in evidence. The timeline is long, the process is gradual, but the direction is set. And this realization tightens the picture again. Once the universe loses the ability to form new stars, the future is shaped not by creation, but by endurance. Any remaining light must come from stars that already exist, slowly exhausting their fuel in isolation. From there, attention shifts away from formation entirely toward what follows, when even those last sources of light finally shut down. Part 5. What physically happens when the final star goes dark? Is there a final event, or does the universe simply stop glowing without notice? When people imagine the end of starlight, they often picture a moment, a last flash, a final signal, some decisive cosmic shutdown that marks the boundary between a bright universe and a dark one. Modern astrophysics points to a very different picture. There is no universal alarm, no synchronized ending, no physical mechanism capable of announcing that the last star has crossed a line. What happens instead is quieter, slower, and far more difficult to locate in time. The reason lies in how stars actually die, especially the stars capable of surviving longest. As established earlier, the final sources of light are not massive stars that explode, but low-mass stars that fade. When such a star exhausts its nuclear fuel, the change is not abrupt. Fusion reactions weaken gradually. As hydrogen in the core becomes scarce, energy production declines, pressure support decreases. The star contracts, slightly heats internally for a time, and then settles into a long cooling phase. From the outside, the star simply grows dimmer. The last star cools into a black dwarf invisibly. A black dwarf is not a new object in the way a neutron star or black hole is new. It is the endpoint of a white dwarf that has cooled so thoroughly that it emits almost no detectable radiation. Importantly, no black dwarfs exist yet. The universe is not old enough. White dwarfs themselves take trillions of years to cool to that stage. The concept is a projection, but it is a projection grounded in well-tested physics. The path to a black dwarf begins with a white dwarf, which forms when a low or intermediate mass star sheds its outer layers and leaves behind a dense core supported by electron degeneracy pressure. That pressure is a quantum mechanical effect arising from the behavior of electrons packed into a small volume. White dwarfs shine not because they are generating energy, but because they retain heat from earlier nuclear burning over immense timescales that heat leaks away. Cooling curves for white dwarfs have been studied extensively. Astronomers use them as cosmic clocks. By measuring the temperatures of white dwarfs in star clusters of known age, researchers test models of stellar evolution. These models consistently show that cooling slows over time but never stops. Given enough time, every white dwarf will approach thermal equilibrium with its surroundings. At that point, it becomes effectively dark. The final star, if it follows this path, does not switch off. It drifts into invisibility. There is no flare, no collapse, no radiation spike. From any nearby vantage point, there is no event to mark the transition. The star simply becomes harder to detect than impossible. This alone challenges the idea of a definable cosmic ending. But there is a deeper reason. The universe offers no clear moment when the last star goes dark. It lies in the nature of time itself. In Einstein's framework, time is not absolute. It depends on motion, gravity, and space-time geometry. Different observers experience different time intervals between the same events. In cosmology, this becomes especially important because observers in different regions of the universe are not only moving relative to one another, but are embedded in an expanding space-time. When astrophysicists assign ages to cosmic events, they usually do so using cosmic time defined within a specific model of the universe. This model assumes a homogeneous and isotropic universe on large scales and uses the expansion history to define a shared temporal coordinate. This is an extraordinarily useful tool. It allows astronomers to say that galaxies formed at certain epochs, that star formation peaked at a certain age, and that the universe is approximately 13.8 billion years old. But it is still a coordinate choice, not a universal clock that every observer must agree upon. This limitation becomes unavoidable when discussing the last star. Suppose a red dwarf in a distant galaxy finally exhausts its fuel and cools beyond detectability. In its local frame, that process unfolds smoothly. For a distant observer, the information about that fading arrives delayed by the time it takes light to travel across expanding space. For another observer, elsewhere, gravitational effects further alter the timing. There is no single instant when all observers can agree that the last star has gone dark. This is why the phrase "final star" must be handled carefully. It does not describe a moment shared across the universe. It describes a boundary in physical processes. It marks the point beyond which no star anywhere is capable of sustained nuclear fusion. That boundary is not crossed everywhere at once. It is crossed locally, independently, and without coordination. The quotation from Kip Thorne captures this constraint with precision. Time is not absolute, it depends on the observer. In astrophysical terms, this means that even if we could identify the last fusion reaction anywhere in the universe, we could not promote it to a universal ending. The universe does not have a master timeline that declares completion. Historical work in relativity reinforces this view. Early debates over simultaneity showed that even simple events like two flashes of light occurring at different locations, could not be assigned a single order without specifying a frame of reference. In an expanding universe, the problem is magnified. Expansion introduces horizons beyond which events can never be observed at all. Some stars that form and die in distant regions will never be seen from elsewhere, no matter how long one waits. This has direct consequences for how cosmic darkness unfolds. The sky does not dim uniformly. Some regions lose their stars earlier, others retain them longer. The universe becomes a patchwork of fading light with no central authority to declare the end. From an observational standpoint, this means there will be no last photograph of a starlit universe. There is no final dataset, no last survey. Each observer's accessible universe shrinks over time as expansion carries distant regions beyond causal contact. Long before the last star fades, most stars will already be unobservable to most observers. This leads to an important clarification. Cosmic darkness is not the absence of matter. It is the absence of accessible energy gradients. Stars are visible because they maintain large temperature differences between their cores and surroundings. When those gradients disappear, light production collapses, matter remains, structure remains. But the processes that generate detectable radiation are exhausted. Astrophysical models predict that after the era of starlight, the universe enters a phase dominated by stellar remnants. White dwarfs cool. Neutron stars lose residual heat. Black holes persist as gravitational structures, not light sources. Background radiation continues to redshift and cool. None of this requires a trigger event. It is the natural continuation of known physics. It is worth noting that even the concept of black dwarf is a label of convenience. It describes a state, not a discrete object class. A white dwarf does not become a black dwarf at a specific temperature. It gradually approaches darkness. The threshold is defined by detection limits, not by physics itself. This perspective also explains why the end of starlight cannot be dated in the same way as earlier cosmic milestones. The recombination era, when the cosmic microwave background was released, can be assigned a specific age because it was tied to a well-defined physical transition that occurred everywhere under similar conditions. The end of starlight is not like that. It is decentralized. It is asynchronous. It is shaped by local histories and global expansion together. In this sense, the universe does not stop glowing. It simply stops producing new sources of glow. Existing light continues to travel. Photons, emitted long before the last star fades, continue moving through space, stretched to longer wavelengths by expansion. For a time, even after the last fusion reaction, there will still be light in transit. Darkness is not immediate. It accumulates. The distinction between emission and observation is crucial. Emission ends locally. Observation fades gradually. This separation ensures that there is no clean boundary where light suddenly ceases to exist. The idea that there is no cosmic moment may feel unsatisfying, but it is one of the most robust conclusions modern cosmology offers. It arises not from ignorance but from precision. The equations that describe space-time forbid a universal ending timestamp. The physics of stars forbids a dramatic shutdown. Together they remove the possibility of a final event. As a result, the end of starlight is not something the universe experiences. It is something that different regions approach independently, without awareness of one another. Darkness does not arrive, it accumulates. And once that accumulation is complete, when no star anywhere can sustain fusion and no remnant retains meaningful heat, the universe enters a regime where change is sharply limited. Attention shifts away from stars altogether toward how matter and space-time behave in a cosmos where light itself has become rare. Part 6. After the last star, is anything still happening? If nothing shines, does physics continue to operate? At first, the question feels almost unfair. We are used to reading the universe through light. Stars mark structure. Radiation reveals motion. Energy differences tell us where processes are active. When the last star goes dark, it is tempting to imagine that physics itself has reached an ending. But modern cosmology gives a far more precise and far more demanding answer. Physics does not stop. What disappears is not activity, but the conditions that make activity fast, structured, and easy to observe. The universe after the last star is known as the post-stellar universe. This term does not describe emptiness. It describes a change in regime. The dominant sources of free energy, the engines that once drove rapid transformation, are gone. What remains are remnants, fields, and fundamental interactions, operating under severe constraints. To understand this phase, it is essential to separate light from dynamics. Light is only one way matter and energy interact. Nuclear fusion produces light efficiently, which is why stars dominate our picture of cosmic activity. When fusion ends, electromagnetic radiation no longer serves as the primary messenger. But gravity, quantum mechanics, and thermodynamics continue to function exactly as their equations require. Quantum and gravitational processes persist extremely slowly. Nothing in known physics allows these processes to switch off. Particles still exist. Fields still fluctuate. Mass still curves space-time. What changes is the timescale. Consider gravity first. After the stellar era, matter is concentrated in compact remnants. White dwarfs, neutron stars, and black holes dominate the mass distribution within gravitationally bound regions. These objects continue to interact gravitationally. Orbits remain stable. Weak encounters still occur. Over immense spans of time, gravitational perturbations slowly rearrange systems. Stars that once orbited peacefully can be ejected from galaxies through repeated weak interactions, a process already observed in globular clusters today. This continues long after starlight ends. Black holes in particular become central actors. Supermassive black holes remain at the centers of galaxies, with masses reaching billions of times that of the Sun. Their gravitational influence shapes the motion of surrounding remnants. On very long timescales, black holes themselves are not static. According to theoretical work by Stephen Hawking, black holes emit radiation due to quantum effects near their event horizons. This process, known as Hawking radiation, causes black holes to lose mass extremely slowly. For stellar mass black holes, the evaporation time exceeds 10 to the power of 67 years. For supermassive black holes, the timescales are vastly longer. Yet the key point is that even the most stable structures known are not eternal under known physics. Quantum processes also persist. At the smallest scales, particles obey quantum rules regardless of cosmic brightness. Virtual particles continue to appear and disappear. Quantum tunneling remains possible. Radioactive decay, where applicable proceeds according to fixed probabilities. These processes do not require stars or light. They require only the existence of quantum fields, which remain as long as space-time exists. However, while these processes continue, they do so without coordination. There is no mechanism left to amplify small changes into complex structures. Without free energy, complexity collapses permanently. Free energy is the ability to perform work. It arises from gradients, differences in temperature, density, or chemical potential. Stars create enormous gradients. Their hot cores and cooler surroundings drive radiation, chemistry, and structure. Once stars are gone, these gradients flatten. Systems approach equilibrium. This is where entropy becomes the dominant concept. Entropy is often misunderstood as disorder, but in physics it is more accurately described as the spreading out of energy. In the post-stellar universe, energy is still present, but it is evenly distributed. Without strong gradients, processes slow to a crawl. Nothing forbids change, but nothing encourages it. This idea did not originate in cosmology. It emerged from 19th-century thermodynamics, when physicists studying heat engines realized that systems naturally evolved toward equilibrium. Later, this insight was extended to the universe as a whole. When applied carefully, it suggests that the long-term fate of the universe is a state where no significant energy differences remain to drive macroscopic change. This scenario is often called heat death, not because everything is hot, but because usable energy has been exhausted. Observational evidence supports the direction of this evolution. Measurements of the cosmic microwave background show that the universe is cooling as it expands. The background temperature decreases steadily. Star formation rates decline. Energy production becomes rarer. Each observation points toward a future where energy flows diminish. Importantly, heat death does not mean the universe disappears. Matter remains. Space remains. Time continues locally. But the capacity to build, to transform, to sustain complex systems fades. This is why the sentence that anchors this part is precise. The universe does not vanish. It loses the ability to change in interesting ways. The phrase "interesting ways" is not a value judgment. It refers to processes that generate new structure, new gradients, or new information at macroscopic scales. In the post-stellar universe, most change occurs at microscopic or gravitationally diffuse scales. These changes are real, but they do not accumulate into complexity. There is a historical reason scientists are cautious when discussing this phase. In the early 20th century, some cosmological models predicted recollapse or cyclic behavior. In those scenarios, a dark universe could reignite. Modern observations have largely ruled these out. Accelerated expansion prevents large-scale recontraction. Once gradients are gone, known physics offers no path to restore them. Experiments continue to test the limits of these conclusions. Particle physicists search for proton decay, which would alter the long-term composition of matter. So far, no confirmed decay has been observed, placing lower bounds on proton lifetimes exceeding 10 to the power of 34 years. If protons are unstable, matter itself slowly dissolves into radiation, reinforcing heat death. If protons are stable, matter persists longer but without energy gradients. Persistence does not imply activity. There is also ongoing research into dark energy. Its nature remains unknown. However, current measurements indicate that it behaves consistently over time, driving continued expansion rather than reversal. Unless future observations reveal a dramatic change, expansion will continue isolating matter and diluting energy. The post-stellar universe is therefore not a stage of mystery because we lack equations. It is a stage of clarity because the equations converge. Gravity smooths structure. Quantum effects erode the most stable objects. Thermodynamics flattens gradients. Each field contributes to the same outcome through different mechanisms. This convergence is what gives cosmologists confidence in describing events trillions or even quadrillions of years in the future. While the exact timeline depends on details, the direction does not. The universe becomes quieter, not because laws fail, but because they succeed too well at driving systems toward equilibrium. It is also important to recognize what does not happen. There is no sudden silence, no universal freeze, no final frame where motion stops. Change continues, but its scale shrinks. Processes stretch across spans so long that they defy ordinary intuition. A single orbital perturbation may take longer than the entire stellar era to complete. A single quantum decay may outlast galaxies. In this way, the post-stellar universe is not static. It is asymptotic. It approaches stillness without reaching it in finite time. This understanding emerged gradually through decades of work linking astrophysics, particle physics, and thermodynamics. It was not derived from one observation, but from consistency across many. Each field working independently arrived at the same conclusion. And that conclusion shifts attention again. Once stars have vanished and complexity has thinned out, the structures that continue to dominate mass and curvature begin to stand out. The universe is no longer organized around light, but around the behavior of its most persistent and compact objects. What remains is shaped increasingly by how black holes influence everything that is left. Part 7. Do black holes become the final structures of the cosmos? When stars disappear, who holds matter together? Once the era of starlight fades, the architecture of the universe does not dissolve. Gravity continues to organize what remains. But the objects responsible for that organization are no longer stars. They are black holes, the most compact and massive structures produced by known physics, and the only ones capable of dominating cosmic structure long after every star has vanished. Modern astronomy has established that nearly every large galaxy hosts a supermassive black hole at its center. Observations from NASA ESA and the James Webb Space Telescope show that these objects possess masses of billions of solar masses, where a single solar mass is about 2 × 10⁻30 kilograms. These black holes, formed early, grew rapidly through mergers and accretion, and now sit at the deepest gravitational wells their galaxies can offer. As stars disappear, these black holes do not lose relevance, they gain it. With no new stars forming and old stars fading into remnants, mass becomes increasingly concentrated in compact objects. White dwarfs and neutron stars populate the outskirts, but black holes dominate the gravitational hierarchy. Over time, gravitational encounters cause smaller remnants to drift inward, to be captured or be ejected. Galaxies slowly relax into configurations where black holes anchor what little structure remains. This leads to the first hypothesis. Black holes dominate structure until evaporation. For immense spans of time, black holes act as the primary organizers of matter. They bind surrounding remnants into loose systems. They merge with one another during rare encounters. They persist, while other objects cool, fragment, or disperse. In this sense, the universe enters what many cosmologists call the black hole era. The physics behind this dominance is straightforward. Black holes are stable because no known force can dismantle them efficiently. They do not rely on nuclear fuel. They do not radiate away energy in bulk through ordinary processes. Their defining feature, the event horizon, isolates their interiors from the rest of spacetime. For classical physics, that horizon is absolute. For decades, this picture suggested that black holes might be the final survivors of cosmic evolution. If everything else fades, black holes would remain quietly curving spacetime forever. That expectation was overturned not by observation but by theory. In the 1970s, Stephen Hawking demonstrated that black holes are not perfectly black. Quantum mechanics applied near the event horizon predicts that black holes emit radiation. This radiation is extremely weak for large black holes, but it is real. Over time, it causes black holes to lose mass. Hawking summarized the idea in a characteristically direct way. Black holes ain't so black. Hawking radiation erodes even the most stable objects. The process is slow, beyond ordinary comprehension. A stellar mass black hole takes far longer than the current age of the universe to lose even a fraction of its mass. Supermassive black holes persist for timescales that exceed 10 to the power of 100 years. Yet the direction of change is unambiguous. Given enough time, black holes evaporate. The mechanism does not require formulas to understand its consequence. Quantum fields near the event horizon fluctuate. Under certain conditions, energy is carried away from the black hole. the black hole shrinks. Smaller black holes evaporate faster than larger ones, so the final stages of evaporation accelerate as mass decreases. The key point is not the details of the process, but the inevitability implied by it. This realization reshaped cosmology's view of the far future. Black holes are not eternal anchors. They are long-lived but not permanent. Their dominance defines an era, not an endpoint. Observational evidence supports the existence and properties of black holes, even if Hawking radiation itself remains too weak to detect directly for astrophysical black holes. Measurements of stellar orbits near galactic centers confirm extreme compact masses. Gravitational wave detections reveal black hole mergers exactly as predicted by general relativity. Accretion disks and relativistic jets map the behavior of matter near event horizons. All these observations reinforce the reliability of black hole physics as a foundation for far future predictions. The story behind these discoveries adds depth to the picture. In the early 20th century, black holes were mathematical curiosities. Even Einstein doubted their physical reality. It was only through decades of theoretical development and observational breakthroughs that black holes became accepted as real astrophysical objects. Ironically, just as black holes became central to our understanding of cosmic structure, quantum theory revealed their ultimate vulnerability. During the black hole era, the universe does not become chaotic. It becomes simplified. Structures merge or evaporate. Motion continues, but it is dominated by gravity rather than radiation or chemistry. The pace of change slows dramatically. A single black hole merger may be separated from the next by spans of time that dwarf the entire stellar era. One might ask whether black holes truly hold matter together in a meaningful sense once stars are gone. The answer is yes, but only locally. Black holes bind what remains within gravitationally bound regions. Beyond those regions, accelerated expansion continues to separate matter irreversibly. The universe becomes a collection of isolated islands, each centered on massive remnants, drifting apart faster than gravity can reconnect them. This interplay between black hole dominance and cosmic expansion is crucial. Black holes control structure inside galaxies and clusters. Expansion controls structure between them. Neither negates the other. Together they define the geometry of the late universe. As black holes slowly evaporate, their influence wanes. The final black holes are the most massive ones because evaporation time increases with mass. Smaller black holes disappear first. Over inconceivably long timescales, even supermassive black holes fade, releasing their mass energy back into space as low-energy radiation. At that point, the universe transitions again. It moves beyond the black hole era into a state where no bound structures remain. Matter, if stable, exists as isolated particles spread thinly across expanding space. Radiation dominates energy content, but at extremely low temperatures and long wavelengths. It is important to emphasize that none of this requires new physics. The conclusions follow from combining general relativity, quantum field theory, and observational cosmology. Each piece has been tested independently. Their convergence gives confidence in the broad outline of the future, even if details remain uncertain. Black holes do become the dominant structures of the cosmos for an immense duration. They organize matter when stars are gone, but they do not represent a final state. They are temporary custodians in a universe that continues evolving even when evolution becomes almost imperceptibly slow. This understanding sharpens the problem further. Once black holes evaporate and matter is spread thin, the idea of permanence has to be reconsidered again. Attention moves away from gravity's large-scale structures and toward the stability of matter itself. What comes into focus is whether the particles that make up everything can, in physical terms, persist indefinitely. Part 8. Could matter itself eventually disappear, What if atoms are only temporarily stable? For most of human history, matter felt permanent. Stones endure, mountains erode slowly. Atoms, once discovered, appeared even more fundamental, tiny units of substance that could be rearranged but not destroyed. Modern particle physics has forced us to examine that assumption with uncomfortable care. When cosmology looks far beyond the era of stars, and even beyond black holes, it arrives at a question that is no longer astronomical, but subatomic. Does matter itself last forever, or is its apparent stability only temporary on cosmic timescales? At the center of this question is the proton. Protons sit in the nuclei of atoms. They define chemical elements. They give matter its solidity. If protons are stable, then matter can persist long after stars fade and black holes evaporate. If protons decay, then even the most durable structures dissolve not violently, but patiently, particle by particle. The idea that protons might decay did not emerge from cosmology. It came from attempts to unify the forces of nature. In the 1970s, physicists developed grand unified theories that sought to describe electromagnetism, the weak nuclear force, and the strong nuclear force within a single framework. In many of these models, protons are not absolutely stable. They can transform into lighter particles through processes that violate baryon number conservation. The predicted lifetimes were enormous, but finite. This is where numbers matter. Current experimental limits place the proton lifetime at greater than 10 to the power of 34 years. That is not a prediction. It is a lower bound. It means that if protons decay, they do so more slowly than any decay process ever observed. To put this in context, the universe is about 13.8 billion years old. The lower bound on proton lifetime exceeds that age by more than 24 orders of magnitude. Such timescales are difficult to reason about, but they are not arbitrary. They are the result of decades of careful experimental work. Large underground detectors, shielded from cosmic rays, have been built to watch vast numbers of protons simultaneously. Water Cherenkov detectors, for example, contain enormous volumes of ultra-pure water. Every hydrogen nucleus in that water contains a proton. By monitoring these detectors over many years, physicists effectively observe on the order of 10 to the power of 34 proton years of exposure. So far, not a single unambiguous proton decay event has been confirmed. This brings us to the first hypothesis. Matter dissolves into radiation. If protons decay, then atoms are not eternal. Over extreme timescales, matter would slowly transform into lighter particles such as positrons, neutrinos, and photons. Structures would not collapse suddenly. They would thin. A solid object, given enough time, would become a diffuse cloud of radiation and elementary particles spread across expanding space. The consequences for cosmology are profound. After stars are gone and black holes evaporate, proton decay would ensure that even remnants do not last. White dwarfs, neutron stars, and isolated atoms would gradually lose their substance. The universe would approach a state dominated entirely by radiation and very light particles, all at extremely low energy. This scenario aligns naturally with the idea of heat death. As matter decays, energy spreads further. Entropy increases. Distinctions fade. There are no gradients left to exploit. The universe becomes simple in composition and uniform in distribution. Yet this is only one possibility. The second hypothesis remains equally consistent with current evidence. Proton stability is absolute, and darkness takes another form. If protons never decay, then matter persists indefinitely. Atoms may be isolated, cold, and inert, but they remain. In this case, the universe after the black hole era contains particles with mass spread thinly across space. Complexity still collapses because energy gradients vanish, but substance itself does not dissolve into radiation. What makes this hypothesis compelling is not that it is optimistic, but that it is supported by experiment. Despite decades of searching, no proton decay has been observed. Every new detector pushes the lower bound higher. Each null result strengthens the case for stability, even as it leaves room for decay at even longer timescales. The story behind these experiments is a lesson in scientific patience. Early grand unified theories predicted proton lifetimes short enough to be detected within a few decades. Those predictions were falsified. Rather than abandoning the question, physicists refined their models. New theories predicted longer lifetimes. Experiments adapted. Larger detectors were built. Observation continued. The absence of decay became data. This process reflects how particle physics informs cosmology. The fate of the universe depends not on speculation, but on the measured behavior of particles. Whether matter disappears or persists hinges on outcomes that can in principle be tested today. It is also important to clarify what proton decay would not do. It would not produce light in any meaningful sense. The radiation released would be extremely low energy by the time it mattered cosmologically. There would be no glow. Darkness would deepen, not brighten. In both hypotheses, darkness dominates. The difference lies in composition, not appearance. In one case, darkness is filled with radiation and ephemeral particles. In the other, it contains cold, isolated matter that no longer interacts meaningfully. From the perspective of astrophysics, both outcomes represent a universe that has lost the ability to build or sustain complex structures. Galaxies are gone. Stars are gone. Chemistry is inactive. What remains is governed by fundamental interactions, operating at minimal intensity. The question of proton decay also highlights an important boundary in our knowledge. Cosmology often deals in vast scales, but it relies on particle physics for its foundations. When those foundations are uncertain, cosmic predictions inherit that uncertainty. This is not a weakness. It is an honest accounting of what is known and what remains open. Research continues. New detectors, such as next-generation water Cherenkov experiments and liquid argon observatories, aim to improve sensitivity by orders of magnitude. If proton decay exists, future experiments may find it. If not, the case for absolute stability strengthens further. Either result would be decisive for the far future of the universe. If decay is observed, the timeline of matter dissolution becomes calculable. If it is not, matter persists as a silent residue long after energy flows have ceased. In this way, the fate of atoms is not an abstract question. It is an active research program. The universe's most distant future depends on measurements made in laboratories today, deep underground, listening for events that may never occur. And once that boundary is reached, when matter either dissolves or settles into permanent inertia, the final constraint on cosmic endings comes into view. Attention moves away from particles themselves and toward the rules that govern energy. What matters then is whether thermodynamics permits any outcome other than the equilibrium that appears to await everything that exists. Part 9. Is heat death the only ending allowed by known physics? Is maximum entropy the final rule the universe obeys? By the time stars have vanished, black holes have eroded, and matter itself stands on uncertain ground. Cosmology reaches a boundary that is not defined by objects, but by laws. The question is no longer about what remains in the universe, but about what the universe is still allowed to do. At this stage, all paths seem to converge on a single concept drawn from thermodynamics: equilibrium, a state where energy differences are erased and no further large-scale change can occur. This outcome is commonly called heat death, and it arises not from speculation, but from the most tested physical principle we possess. The second law of thermodynamics states that in an isolated system, entropy does not decrease. Entropy, in precise terms, measures how evenly energy is distributed. When energy is concentrated, work can be done. When energy is spread uniformly, work becomes impossible. The universe on the largest scales behaves as an isolated system. There is no external reservoir to draw from, no outside gradient to exploit. Every observation of cosmic evolution, from the cooling of the cosmic microwave background to the decline of star formation, is consistent with entropy increasing. In the early universe, energy was unevenly distributed. Matter clumped. Radiation was hot. Gradients were strong. These conditions allowed structure to form. Galaxies assembled. Stars ignited. Complexity emerged. Over time, those gradients weakened. Energy flowed from hot regions to cooler ones. Matter fell into gravitational wells and released energy which then dispersed. Each process increased entropy while creating temporary order. That order was always borrowed. This brings us to the first hypothesis. Classical heat death is unavoidable. Given the laws of thermodynamics as currently understood, the universe evolves toward a state of maximum entropy. In that state, all accessible energy differences are exhausted. Temperature becomes uniform across space. No macroscopic process can extract work. Motion continues at the microscopic level, but nothing accumulates into structure. When cosmologists simulate the far future using known physics, every scenario that does not involve a recollapse leads toward equilibrium. Expansion dilutes energy. Radiation redshifts. Matter cools. Entropy climbs. Observations support this direction at every stage we can test. Measurements by NASA and ESA show that the universe is expanding at an accelerating rate. Data from the James Webb Space Telescope reveal that star formation peaked billions of years ago and has been declining ever since. The cosmic microwave background continues to cool. No observation suggests a reversal. Heat death does not mean the universe becomes hot. It means it becomes unable to support change. Energy remains, but it is useless. Matter remains, but it is inert. Time continues locally, but nothing meaningful evolves. The unsettling strength of this conclusion lies in its independence from detail. It does not depend on whether protons decay or remain stable. It does not depend on whether black holes evaporate quickly or slowly. It depends only on the absence of new energy gradients. As long as entropy increases and expansion continues, equilibrium awaits. Yet physics has taught us caution. Every time we believed a framework was complete, deeper layers emerged. This motivates the second hypothesis. Unknown physics at extreme timescales modifies the outcome. This hypothesis does not deny thermodynamics. It questions its domain of applicability. The second law has been tested in laboratories, stars, galaxies, and the observable universe, but it has never been tested over timescales exceeding 10 to the power of 100 years. At such extremes, effects that are negligible today may dominate. One candidate lies in quantum gravity, a theory not yet complete. At present, general relativity describes space-time at large scales, and quantum mechanics governs particles at small scales. Their unification remains unresolved. It is possible, though unproven, that quantum gravitational effects introduce new channels for energy redistribution or space-time restructuring that alter the ultimate fate of entropy. Another possibility involves dark energy. Observations indicate that dark energy behaves like a constant energy density of space. If that behavior changes over time, the expansion history of the universe could change. A decay of dark energy could slow expansion. A reversal could lead to contraction. So far, no data support such behavior, but the timescales involved far exceed observational reach. There is also the question of vacuum stability. Some models suggest that the vacuum state of our universe is metastable. If a transition to a lower energy vacuum were to occur, the laws of physics themselves would change locally. Such an event would not violate thermodynamics, but it would redefine what equilibrium means. Again, no evidence indicates that such a transition will occur, but the possibility remains within some theoretical frameworks. These alternatives are not predictions. They are placeholders for ignorance. They exist because physics remains incomplete, yet they must be weighed against the overwhelming success of existing laws. Every unknown must overcome a vast body of consistent evidence pointing toward equilibrium. Richard Feynman once remarked, "Nature uses only the longest threads to weave her patterns." In a scientific context, this statement captures the tendency of physical laws to express themselves most clearly over long durations. Thermodynamics is one of those threads. It has survived every test so far. Its reach extends from steam engines to galaxies. If any principle deserves trust at cosmic scales, it is this one. Heat death is therefore not a dramatic ending. It is a limit. It describes what happens when nothing new can happen. The universe does not stop existing. It stops evolving in any structured way. It is important to emphasize that heat death does not occur at a moment. Like the end of starlight, it is not an event. It is an approach. Systems drift closer to equilibrium, asymptotically. They never reach it in finite time. The universe becomes increasingly quiet, increasingly uniform, increasingly indifferent to change. Some early cosmological models proposed alternatives, oscillating universes that expand and contract, big crunch scenarios where gravity reverses expansion. Observational data have steadily eliminated these options. Accelerated expansion rules out recollapse under known physics. The universe is not heading toward compression, it is heading toward dilution. In practical terms, this means that any remaining structures are temporary. Even if protons are stable, isolated atoms, eventually spread beyond meaningful interaction. Even if black holes persist for unimaginable durations, they eventually evaporate. Each process increases entropy. Each removes another gradient. The strength of the heat death scenario lies in its minimal assumptions. It does not require exotic events. It does not rely on rare fluctuations. It follows directly from what is already measured. Yet cosmology remains honest about uncertainty. Unknown physics could intervene. But until such physics is observed or required by inconsistency, it remains speculative. The burden of proof lies with alternatives, not with thermodynamics. As a result, when cosmologists speak of the fate of the universe, heat death occupies a unique position. It is not merely one option among many. It is the default outcome implied by everything we know. This does not make it final in an absolute sense. Science does not deal in absolutes beyond evidence, but it makes it the reference point against which all other endings must be compared. And with that realization in place, the final issue comes into focus. If heat death is not an event, if it requires no observer, and if it unfolds without any distinct moment, then the idea of an ending itself needs to be reconsidered. What remains is the question of what it actually means to say that the universe ends at all. Part 10. If no one observes the end, does the universe still end? Can an ending exist without a witness? By the time cosmology reaches this question, almost everything familiar has already been removed from the picture. Stars no longer shine. Galaxies no longer build structure. Black holes, once the deepest anchors of gravity, are themselves fading. Matter may persist or dissolve, but either way, energy differences are gone. What remains is a universe governed by laws that continue to operate even when there is nothing left to observe their effects. This is where the limits of observation become inseparable from the limits of prediction. Physics is built on measurement. Every law we trust has been tested by observation directly or indirectly. Yet the far future of the universe stretches beyond any possible observer. No telescope can be built to watch it. No experiment can be repeated there. The question is not philosophical. It is operational. Does physics still describe an outcome when observation is no longer possible? To answer that, we must first clarify what observation means in physics. Observation is not consciousness. It is interaction. A detector registers a particle. A sensor absorbs a photon. A measurement occurs when information is physically recorded. Nowhere in fundamental physics is there a requirement that this information be seen, remembered, or understood. The equations that describe motion, decay, expansion, and equilibrium do not check whether an observer is present. Physical processes continue without reference to meaning. Stars do not burn because they are watched. Black holes do not evaporate because they are measured. Expansion does not accelerate because someone records it. These processes occur because the laws governing matter and energy permit and require them to occur. Evidence for this view is already embedded in everyday astrophysics. Many events happen beyond our observational reach. Stars form inside opaque clouds long before their light escapes. Black hole mergers occur in distant galaxies without emitting light at all, detectable only through gravitational waves, if detectors happen to be sensitive and aligned. Nuclear reactions inside stars proceed regardless of whether their photons reach a telescope. Observation is contingent. Physics is not. This distinction becomes absolute in the far future. As expansion continues, more regions of the universe pass beyond causal contact. Events occur that can never be observed by any future observer, no matter how patient or advanced. Yet no physical theory suggests that those events fail to happen. On the contrary, general relativity predicts them precisely. Observation plays no role in cosmic fate. The universe does not wait to be seen in order to evolve. Its equations define trajectories, not audiences. This is not a speculative claim. It is a direct consequence of how modern physics is structured. The fundamental laws are local. They describe how fields and particles behave at each point in space-time. They do not contain global conditions that depend on knowledge, memory, or record-keeping. Consider cosmic expansion. The expansion rate is determined by the energy content of the universe: dark energy, matter density, radiation density. These quantities evolve according to equations tested through observation by organizations such as NASA and ESA, using data from missions, including the James Webb Space Telescope. Nowhere in those equations does an observer appear. Expansion proceeds even in regions where no structure exists to observe it. The same is true for thermodynamics. Entropy increases because there are more ways for energy to be spread out than concentrated. This statistical tendency does not require awareness. It emerges from probability and scale. Whether or not anyone counts microstates, the distribution evolves. The end of the universe, as described by known physics, is therefore not an event that needs to be witnessed. It is a condition that is approached. Heat death does not happen at a moment. It becomes true gradually, locally, irreversibly. At some point, no process capable of sustaining observers remains, long after that physical evolution continues. This realization often triggers confusion because of how quantum mechanics is sometimes discussed. In certain interpretations, measurement plays a role in defining outcomes. But even here, the role of measurement is frequently misunderstood. Measurement in quantum mechanics refers to interaction with a macroscopic system, not to observation by a conscious entity. A detector counts, a particle scatters, a state becomes correlated with an environment. Consciousness is not required. Moreover, quantum mechanics itself operates within space-time. It does not override thermodynamics or cosmology at large scales. Whatever interpretation one prefers, none imply that the universe ceases to evolve without observers. They imply limits on what can be predicted or known, not on what occurs. Early debates about the universe often mixed observation with existence. Before telescopes, many celestial objects were unknown. They still existed. Before gravitational waves were detected, black hole mergers occurred unnoticed. They still shaped space-time. The universe has always done far more than has ever been observed. In the far future, this asymmetry becomes complete. There will be no observers. Not because the universe ends, but because the conditions required for observers vanish. Complexity requires free energy. Memory requires structure. Measurement requires gradients. When those disappear, observation ends. Physics does not. This brings us to the final sentence that anchors this entire journey. The universe does not require memory-only laws. Memory is a physical process. It depends on stable structures, energy differences, and irreversible changes. In the post-stellar post-structural universe, memory cannot persist. Records decay. States homogenize. Information disperses. But the laws that govern these processes remain embedded in space-time itself. From the perspective of cosmology, this is not bleak. It is precise. The universe does not collapse into nothingness. It does not stop. It continues according to rules that no longer generate novelty. This is why the question of whether the universe ends without observers has a clear scientific answer. The universe does not need an ending in the narrative sense. It transitions into a state where nothing new happens on accessible scales. That transition does not depend on witnesses. If one were to define the end of the universe operationally, it would be the point beyond which no physical process can support observation. Not because physics fails, but because it succeeds too thoroughly at flattening differences. All available evidence supports this view. Observations of expansion, entropy, growth, star formation, decline black hole evaporation, and particle stability converge on the same conclusion. The universe evolves toward a quiet equilibrium regardless of who is there to notice. From here on, there is no final moment to describe, only the persistence of physical law. Not with a final flash, not with silence imposed from outside, but with continuity. Laws persist. Change diminishes. Observation fades. The universe remains. Thank you for spending this long night of curiosity here, following the universe, from its bright youth to its distant, quiet future. Your time and attention are deeply appreciated. If this exploration brought even a small sense of calm or clarity, I'm grateful you shared it. Wherever you are listening from and whatever hour has carried you here, I hope the rest of your night is gentle and untroubled. Good night.